All right, thanks everybody for coming. I was really excited earlier when there was no one here, so now that folks are here. So my name is Josh. Nice to meet everyone. I think I've met a lot of you guys throughout the years. I started my career in the AR space. I worked for Daiquiri way back when, and then for Magic Leap. So it's been fun seeing AWE grow from a little small group of people, right, where we all knew each other and interacted, to now there's people from all over the world, all different industries, so it's good stuff. So as Josh talked about, I'm the Chief Revenue Officer and President of Dispelix. This is going to be a little bit technical, so it's a little strange that a business person is up here talking, so I apologize beforehand. So those of you who are technical, please bear with me just a tad. I've successfully all these years gotten out of speaking at AWE because of the technical audience. Working for a Finnish company. Our company is based out of Helsinki. It was a company called a city called Espoo, which is right outside of Helsinki. And my CEO called me one day and said, "Hey, you're in town. You should go ice fishing with me." I'm from LA, so I was like, "Sure, why not?" So he takes me out on snowmobiles out on the ice out in Finland. And right before we get in the ice, there was water. And so he stops at the beach, and it was him and his 14-year-old son and myself. And he said, "Josh, there's water in between, so you have to hit the gas really hard and go." And so we went, and I'm like freaking out because there's water on top of the ice. And I'm thinking we're gonna die. And he takes me way out in the middle of nowhere, like way past all the other people who are fishing. And he stops and drills the hole, and we're fishing. And then a big icebreaker boat goes by like 300 yards away. And he said, "If the water wasn't here, we'd hear the ice cracking under your feet." And I said, "Auntie, why are we here? Like we have to leave right now." And he says, "You're speaking at AWE." And I said, "I don't care, whatever, like that's fine. We have to go." And in Finland, when you say you're gonna do something, you have to do it. And so now you're stuck with the business guy. So I apologize beforehand, but we're here to talk about how can we level waveguides up. What does that mean? Just a little hint towards the end, we're gonna really show you some simulations. We're gonna show you our first sims of what we've done by attacking some problems that are traditionally happen when a waveguide and a light engine are optimized separately. We've now combined it, and so we're trying to do them together. So we're gonna show you our first simulations, and we're gonna just talk about it. Now, when I go through all of that, it's food for thought, if that makes sense, right? It's our first one. So it's gonna get better, but all of us together in the industry can make that happen. So is this my clicker here? All right. Perfect. All right, so Dispelix, we were founded in 2015. Again, we're located in Espoo, Finland, which is right outside of Helsinki. If you have a chance to go, it's amazing. We also have offices in the USA as well as in China. So as you can imagine, with a company that's solely focused on the design and development, prototyping, and fabless manufacturing of waveguides, we focus specifically in that area, and our patents are right around that as well. So everything we do is to develop waveguides. Our mission is to really make sure that the end users of augmented reality devices, that it is a seamless transition from technology to comfort and to interaction with the content in a natural way. Sorry, I lost my screen there. So in order to do that, we have to have a seamless augmented reality transition and a seamless waveguide transition. We'll talk in a minute about our comfort of how we develop and why we develop the way we do. But in today's world, the customers, our end users, they're very technology savvy. All of you have 1 or 2 phones in your pockets or other gadgets and devices. All of us are used to everything working. If you switch from your phone, from your iPhone to your tablet, or from your Android to your Windows, everything just works. It's seamless. The displays are very, very good. They're pretty. It looks great. So consumers expect the exact same thing. In a wearable, in today's world, there's an awful lot of technology that are involved. Prescription lenses, sensors, light engines, waveguides, wireless, battery, et cetera, et cetera, et cetera. On top of that, it has to weigh right around 50 grams. Very, very light. Oh, and by the way, it also has to work for a whole day, right, on one charge, right? And there's more, and there's more, and there's more. Everything, there's so much packed into it. It's very, very tough to do. Now, for us, we believe that it's our responsibility to make sure that the real estate that we take up, which is the waveguide, and also with our partners, the light engines, it's a significant portion of these wearables. It's also what the end user actually looks through, and that's how they tend to gauge and to judge the success or the failure of that device. So we're going to go a little high level, so if any of you are waveguide designers, bear with me. If you're not, then we'll try to make it a bit easier. So this is a waveguide, right? If you look in the upper right-hand corner, there's a little circle, right? So that's an IC or an ink coupler. So that is where we couple with a light engine. That light engine, it projects light and content or a digital image directly into the waveguide. And then from there, we have what's called etchings. So that's like, imagine little grooves that are put into the waveguide. If you've had demos of other companies that are out there, you'll see like a square, right? And so what happens is the light will go into the ink coupler, and then it'll move through and it'll bounce around inside the glass itself or plastic, right, for plastic substrates. And then it'll go into the eye box, and then it'll come out of that into your eye. So then you can see the content. So what we do is we control the light and make it as seamless as possible. So when we design a waveguide, again, we're going to get to the simulations in a minute, but we have to make sure you understand how we think and what we do and why we do what we do for it all to make sense. So we focus on these three things when we design waveguides: social comfort, wearable comfort, and visual comfort. So for social comfort, it's all about the aesthetics, right? It has to have a small grading footprint. So remember I talked about that little square, or you might see some triangles or some rectangles. It has to be extremely small. On top of that, it has to look and feel like normal glasses. So if you see you have a little wrap and you have a little tilt, it can't be a flat surface, and it can't be too far away or too close to your eyes. So when you have a small grading footprint, you can fit all different faces, all different sizes, by just making the cuts different to make it smaller or larger. Eye contact is extremely important as well. So right now, if I'm looking at everyone here, if you can't see my eyes and I can't see your eyes, it's just not a good experience for anybody. On top of that, you also have to minimize the ambient light reflection from the gratings themselves. So imagine if I'm standing here and I have my gratings and you guys just see a square, right? The gratings, they have to be hidden. They can't be something that everyone can see. So, and that's whether if it's on or if it's off. And on top of that, you have to have privacy. If you're in the enterprise space, or if you're aerospace and defense, or if you're a consumer, if I have my content being shown and I'm looking at all of you and you can see what I'm looking at, or you see a big green eye glow, nobody wants that, right? So for privacy purposes, you don't want people to see what you're looking at, and they don't want to see what you're looking at either. For wearable comfort, thin single-layer design. So Dispelix, we specialize, and we've been known for years to create what's called a single-layer waveguide. So that's one thin piece of glass. Weight is extremely important. To cut down on weight, right, it's not about the size, it's about how thin can you actually make it. A single-layer design for years was very difficult to do. Most companies who design waveguides for a long time, they had what's called a 3-layer design. They had one layer of glass for green, one for blue, right? One for red. What Antti Sanari, our CEO, and Juuso, our chief scientific officer, they focused on doing all that in just one layer. Now, a lot of companies have kind of caught up, and they're doing it as well. But to have a very thin single-layer design allows you to have a light waveguide so your glasses look and feel normal. So for balance, how many of you have had a demo of an AR device where it's so heavy in the front you feel like it's going to fall off, right? I think all of us have, right? Or in order to make it work, you have to have a strap up on your head, right? Because the balance is all crazy. a lot of that has to do with where the ink coupler is. So remember that little circle in the corner where the light couples with the light engine? We have moved ours up into the upper right-hand corner. Now, as a company, what we do is a little bit different. A lot of waveguide companies out there, they make a waveguide and they sell it to every single company. It's the exact same waveguide with very minor changes here and there. What we do, it's a little different. We put out a reference design. And so if you come to any of our booths that shows, we demo that, and everyone can try it, and that's what it's for, right? We then take that to our largest customers, whether it's consumer or aerospace and defense, and say, here's a demo. What do you like? What don't you like? Let's build yours. So that's what we do. We build custom design waveguides from the ground up, or we can take one that we've already done and make some configurations if we want to speed it up. So why that's important here for balance is that we've been doing this since 2015, and we have done countless NRE projects or custom design projects. So in our reference designs, so in those pictures that I showed you, you're not stuck having the IC just in that corner. You can move it to where you need it to make sure with your wearable design that it actually fits and it's comfortable and it's well balanced. On top of that, it's all about the tilts and the angles. So when we design our waveguides, we know that people are from all over the world, right? So our eyes are different locations, our faces look different, everything is different. So the waveguide, you have to have the right tilts and angles to match the human face. So it can't just be the exact same flat surface. And then also hopefully I don't stutter this wrong because I struggle with this word all the time, interpupillary. Got it. So I stutter on that word every time. So the distance, right? That's the distance, like this, right? We have to make sure that the eye box is big enough that it's comfortable for everybody. For eye relief, the natural side profile. So if you look at here, this is actually our director of marketing, Haney. Haney's wearing a pair of glasses. And on these glasses, if you look, it's not too far away and it's not too close. It needs to have an airy feel. A lot of augmented reality devices, they're either way out here or they're so close it's uncomfortable. So when you design a waveguide, it's not just simply going to a lab like a lot of colleges and just busting out a waveguide. You can't. You have to spend thousands upon thousands of hours of understanding how humans actually wear glasses and what's comfortable and what's not. So lastly, for visual comfort, we talked about the eye box just a little bit. And for those of you who are unfamiliar, the eye box is when you look through a pair of glasses, AR glasses. Have you ever worn a demo sometimes where you have to squint or move kind of funkily to actually see what's there, right? That's an eye box. With us, we make sure that the eye box is natural. It's big, right? It has to work for everybody, regardless of how their eyes are sitting on their face, regardless of if they have a thin face or they have a wider face, or if, whatever. It has to work. It has to be comfortable. And so it has to be unrestrained for the entire field of view. Brightness. This is the big one for everybody. It's got to work indoors. It's got to work outdoors, right? It's hard to compete with the sun. It really is. We're getting close, but it has to work both inside and outside. And sharpness. So again, if you think of all the years of augmented reality, when companies are coming out with their devices over the next couple years, the consumers, well, frankly, they need to be trained. They need to understand how to use the technology. So some companies are going to be coming out with just text. Some companies are going to be coming out, and that text will be small, it'll be large. Maybe there'll be some imagery, right? Some arrows, some icons, things like that. Other companies, maybe they'll just put out some videos, right? Maybe, whatever their app's going to be. Other organizations are going to do full immersive mixed reality. So your waveguides need to be able to support all of that because the application infrastructure and the ecosystem is going to have all that available. So your waveguides have to be able to work with the tiniest print or a full immersive experience. So that's how we think when we develop. So in a second, we're going to get into the simulation, and we're going to talk about what we're proposing for the industry. But before we go there, just in case there's folks here who are unfamiliar with light propagation in diffractive waveguides, which is what we build, okay? So remember that little circle in the corner, the in coupler? That's where the light engine and the waveguide are coupling. So that's over on your right-hand side there. So light will come into the IC or the in coupler, and then the light and the image is inside the waveguide, inside those gratings that we talked about. And then it's bounced around, and that light is moved, as well as that image, through what's called an EPE, or an exit pupil expander. Then it gets moved again, all that light, all that content, over to an OC, or an out coupler. And then that content, that light, that imagery, will then be pushed to your eye. So, depending on the colors, if it's red, if it's green, if it's blue, there are different distances in how they jump. So we'll show you here. So as you can tell here, the red have longer bounces, longer jumps. The blues are a little bit shorter, and the greens are kind of a mix in between, as well as they're on different frequencies. So things are different. So you have an in coupler, again, goes in and it goes through. So this is a single layer full color waveguide. Now, when you do a single layer full color waveguide and you are trying to get it as bright as you possibly can, you have some uniformity issues that come in. So it's called non-uniformity. So when we design our waveguides and we do our gratings, we build them from the ground up to deal with those non-uniformities from the very beginning. Now, the traditional approach of dealing with non-uniformities is done in two separate areas. The first area is with the light engines, right? So a light engine, in a minute I'm going to talk about Edward Tang from Waveguide. They do fantastic work. We're big fans of the direction that they're going. So we're going to show actually one of his slides. Excuse me. So a projector company like Waveguide or like Coretronic or like Trilight, right? Whether it's LCOS, DLP, LBS, or micro LED. All of them have to focus on white balance, spatial illumination, uniformity at the exit pupil, and then maximizing their power output. So again, remember we talked about those 50-gram waveguides have to actually work for a full day? It's tough, right? Especially when you have to do red, green, and blue. In the waveguides, we focus on our grading designs to combat chromatic grading dispersion, image uniformity, and then brightness and efficiency. So traditionally, they're done separately, right? So one team's working on this, one team's working on that. We work with some of the biggest companies in the world, both for consumer and aerospace and defense. And right now, it's always two separate teams, each trying to solve, frankly, the same problem and similar problems. So what we're proposing is that we actually do it together. So I'm running out of time, so I'm just going to speed this up just a tad. So this is the slide I talked about from Waveguide. Again, they're doing some great stuff. Also, E. Young is also noted here as well. So what you're looking at, upper left-hand corner, is a traditional panel. So a projector or light engine, a light engine will light up the entire panel. So when you light up the entire panel, even though over on the right-hand side, do you see that little alarm clock? That's the piece of content. It's very, very small, just that one area. But the light engine has to light up the entire panel. So as you can imagine, when you do that, the power draw is pretty high, right? But why do we do that? We can do what's called segmented illumination. So that's where we only light up the area where the content is there. When you do that, you save on power, and you also improve your contrast, right? So it's a much better experience. Again, I'm going to kind of speed through this pretty quickly. So we have a three-way process that we are doing it together with a light engine. So light engine and waveguide optimizing at the same time. The first thing that we try to do is to maximize efficiency with no correction whatsoever. So light engine and waveguide are being optimized at the same time. So when you do that, you can significantly increase your efficiency, but when you do it, you lower the uniformity. But that's okay, because we're going to fix it next. Now, the colors with here, for those of you who are designers for waveguides, we've made this obviously different, right? We've made it so you can actually so people can understand, right? So the next step, after we maximize the efficiency and really make it really, really bright, is then we move to what's called segmented illumination. So remember that content where you had that little alarm clock over in the corner? Here, you're seeing that we are fixing some of the uniformity. On the first image, in the upper right-hand corner, you see where it's very, very dark, and then across the middle, it's very, very light. That's that's non-uniformity. So you're not seeing the same thing across every single eye box. So now, at segmented illumination, what you can do is you can increase your efficiency and your uniformity by merging things together. So at this section, we're focusing on those 9 little squares, right? And we're focusing on increasing that uniformity and the efficiency. And then lastly, instead of just the 9 squares, we're going to the pixel level. So when you go to the pixel level, you can go down and actually each pixel individually, you can optimize them. So now you see almost a complete, perfect, uniform area. Now we have left in the upper right-hand corner those 2, so it's easier to understand, right? So we called it out. So now we're going to jump real quick into our simulations. I've got like a minute, so I'll be fast. So for the assumptions, it's a 30-degree field of view for full color, aspect ratio of 16.9, and we've put the area into 3 by 3, and it's optimized for RGB brightness. So what we're looking at here, now we have tweaked the colors just a tad to make it look more like a natural eye. So this is, we've made the eye box into 9 separate areas. We're focusing on the center pupil. So again, we maximize the brightness efficiency with no other correction. But when you do that, do you see how there's different colors across there? That's when you do those, you make it bright, but then you have uniformity problems. Next step, then we fixed it a little bit. We put it into 9 sections, which allowed us to really fix a little bit of that uniformity to make it a little bit closer to perfect. Then we moved it to the last one, where we did segmented illumination and pixel correction at the same time. So at the pixel level, we went to every single pixel individually and optimized the projector and the waveguide at the same time, which then at the center pupil, do you see how the uniformity is? It's really, really good. Now, is it perfect? Not yet. This is our first simulation that we've done. Now, we're going to continue to do this over and over and over again, and we'll continue to work with our partners to make that happen. On micro LED and LBS displays, you can actually go directly to the pixel. You can skip the segmentation, but on DLP and LCOS, you actually have to do all 3. So it's just a little bit different. We've already talked about this. We'll just keep on going. So lastly here, we're big believers in the term YNWA. You'll never walk alone. What that means is it takes the entire ecosystem of AR, whether you're a projector, whether you're a supplier of glass or plastics, or if you're a waveguide company, it takes all of us to work together to truly get to where we need to get to allow these wearables to actually be sold. So that's it. If you have technical questions, business guy, don't forget, feel free to reach out, and I will put you directly in touch with our R&D team, and they'll be more than happy to answer any questions. Thanks, everybody.